So let's get started with the next segment of our agenda for today. The next speaker is Jean-Pierre Panziera, that is now preparing his connection. His position is Chief Technical Director for Extreme Computing at Atos Bull. He has had a long career in the industrial world, and a lot of, if I may say, difficult experience with ARM technology in the HPC world. And he was kind enough to accept an invitation from our side to tell us a few words about this experience and also his perspective on HPC, and particularly HPC in Europe. Jean-Pierre Panziera is also the chairman of the steering board at the ETP for HPC Association, which, as you know, creates the strategic research agenda that is shared with Euro HPC, but other organizations as well. So again, he has a wide range of interests and a lot of experience in actually communicating directions and also the impact of technology-related decisions. So I think it is an honor and a pleasure to have him as a speaker. Jean-Pierre,
Okay.
when ready, please get started. Thank you.
Okay, so just I think I'm showing my screen, and you see the title of this.
Correct.
Okay, and just for me to know, I'm sorry I was not able to come and participate to this workshop in Heraklion. Just how many people in the room, so I have a feeling.
I'm making a rough estimate saying 30, and
30?
there are a couple of. I'm not
Okay.
counting correctly, but roughly like that.
Okay,
no more than
that's good.
30.
So I mean, I just so I was not sure what you had in mind, at least when you invited me for this presentation, but I was very happy to share with you the experience that we had, and more specifically, I want to say. My personal experience. So again, what I'll be talking today, it's my personal recollection and my view on the saga that we went through for the last 15 years. And by no means it does represent any of my company past or present vision or position. So just for this, so it's a personal recollection. So maybe. Just checking the time. So you said 30 minutes, so let's make sure that I don't go over time, because I get passionate about this. I mean, this is something that being kept me busy for the last 15 years. And so maybe you have to go back a little bit and remember what the landscape was back in 2010, so when we all started we embarked in this journey toward delivering solution based on ARM CPUs. If you go back 15 years ago, we were witnessing the era of the end of an era where HPC was dominated by proprietary solutions. And just to name a few ones, I mean, you all remember the Blue Gene, and so in 2010, it was the Blue Gene P. There were follow up a Blue Gene Q, and after that, IBM dropped. But it was, maybe the best example of a solution fully thought with all proprietary technology. Cray also had started, and they based their work on the AMD Opteron, and with the XT series that was a follow-up of the T3E. And they were also delivering very large systems based on a mix of proprietary and third party. Bull, which was a company that I joined the previous year, was finishing what they were calling a cluster made up of super nodes. So SMP was a cluster of SMP, and the SMP node, base node, was 16 sockets. So this was something that was also a mix of proprietary and public, available third party. The SGI, which was my previous company, had actually stopped or was at the end of development of their Altix systems, which was using Intel CPUs, but also a proprietary interconnect that would have a shared memory architecture up to 8K CPU. So it was something big, but it was too expensive, and so it was dropped. And it was dropped towards something that was more commodity. And so this was the ICE clusters, which was a cluster of simple x86 nodes and with InfiniBand. So this was a trend. And actually, it was preceded because, I mean, let's say about the same time, there was this big cluster of x86 nodes that was deployed in China at the NUDT. And at the time, suddenly topped everyone in the top 500. With a 2.5 petaflop. They had what they call proprietary network, but actually everyone, the people that investigated this realized that it was based on some InfiniBand from Mellanox with some of their own source. So this was a situation where we were in a transition between something proprietary and something that was more a more, I would say, commodity. And it doesn't mean that this proprietary architecture completely disappeared, and they were still thriving for a while. And as I mentioned, that there was follow-up the Blue Gene Q. Fujitsu came out with their K computer, which was based on a Spark architecture. They had later on the Fugaku, which was same kind of architecture, but updated with and using an ARM instruction set. And then you had the Chinese with Tianhe 2, which was the last we heard officially about, but there are probably many follow-ups of this. The Cray XT with the MD upturn actually. So I already mentioned that they started using this commodity CPU, and just a reminder that it was this at the time where Intel was pitching the IA instruction set 64-bit, which was something new, and their upturn, AMD with the upturn managed to extend the x86 architecture to 64-bit. So this was quite successful, and in that sense, and it got a lot of attention. So we had these commodity systems using x86 and InfiniBand. It was becoming the big thing, the big wave. But what happened is that after 2010, the AMD roadmap started to become a little more difficult to follow. They had a different roadmap every quarter, and every year someone else was in charge. And after a while, they completely disappeared, and it took them probably until 2017 to come back. On the InfiniBand side, maybe you remember that Mellanox was only one of the provider. They had other options, and it was originally an open standard. And Silverstorm and QLogic were, I mean, just to mention names, and Oracle, Sun had some InfiniBand network that they developed, but that competition disappeared. So what we were left with was the Intel and Mellanox, and they became the standard. And for example, one example, well, a good example of us for this in Europe was the Curry system, which was introduced in end of 2011, and so it was number 9, sorry, in 2012. But the transition from being a reference to becoming a monopolistic is very thin, and that's some impact, as the only provider of a solution, for example, for the CPUs, the costs increase, as a provider because the price follow, and we see this again and again even recently in the domain. And also something was started to be alarming to us as a system designer was that the CPU consumption was, and I remember everyone was really alarmed when the consumption of the CPU, the TDP, went over 100 watt. It used to be 95 for a couple of iterations, and suddenly, it had to go over to 100 watt, and so suddenly people started to be alarmed about this and to think that we needed to take some action. So we needed to look at second source and even better, if possibly, looking for a sovereign alternative. So by sovereign meaning, it's something that you have a good handle on that you control. So this was, very schematically our view of, how we could put together a system and, have this in mind where we had this control. So we were building the racks, and we had put into place the system for with cooling doors, so which means that you would control the airflow and the air temperature in the system, so very good control on this, so you would be able to operate standard nodes, at scale in your data center with a good PUE at the time, about 1.4. The interconnect, so it was, I won't go into the details, but it was about the same time that we launched this BXI, the Bull Exascale Interconnect, and was a proprietary network. We thought we needed to control that. And for the memory, I mean, it was very simple. We had there was a choice of different providers, Micron, Samsung, Hynix, just to mention them. And so there was first thing, there was no need to because there were already three providers, and also we didn't see any way we could get into that very specialized technology, and so we left it like this, making sure that we could use different providers. For the CPU, we started looking at ARMs. It was at the time a very natural move. ARM was, if you remember, it's still based in UK, and if you remember, UK at the time was part of the EU, and so it was a very interesting partner. ARM controlled the ARM instruction set, so this was interesting because and they could license it, and actually they were happy to license it. They were also developing IP and for example, the cores, and so that would be helpful to get you started and accelerate your CPU design. So this was, I think, very interesting, and we started looking at this. But back here, I'm talking about early 2010. At the time, the ARM instruction set was 32-bit. We were dealing with ARM v7 at the time. That was fine for embedded, but it was certainly not appropriate for general computing, and certainly not for HPC. Also, I remember a visit to their headquarters in that time, and it was clear to us that they had absolutely no experience, no idea what were the needs for generic servers at the time, and even less for HPC. Just I remember the stare when I mentioned Fortran, when we're discussing the software part, and nobody in the room during that meeting had an idea what it meant. And you know that it's certainly something crucial for our development of HPC application, even today, but at the time it was central. Okay, so we started looking at this, and there was also very naive thinking, and I heard that several times with my colleagues. Say, what is a good supercomputer with ARM? Well, I mean, you don't need to build one. You have just it's already there. if you go to a rock concert and you have thousands of people with their smartphone, and each a lot of smartphone at the time, and even now, you had some ARM CPUs and Snapdragon, for example, Exynos, and so on. So, and each of them were already delivering hundreds of megaflops. So if you multiply the number of phones by the power of each individual smartphone, you had a petaflop system right away in this event. So that was obviously a little simplistic. And so we started looking into more detail what it meant. And this was a time where Mont Blanc project was started. It was led by Barcelona Supercomputing Center, and in collaboration with ARM. And Bull at the time was the provider of the integrator that was part of this project. So, and what you see here is after many iteration and discussion and what would be the appropriate right platform for the demonstration and of that project. Well, the only solution that we find that was possible was using this Samsung Exynos CPU, which you see the card here there with a €1 coin here, just to give the scale. So you put one of these, you got 27 here in a blade, and you fill a couple of racks with a blade. So you got something which is, I think at the time had about 1,600 core CPUs. And so this was, a big achievement and realization. However, it was quite disappointing because it was still, the 32-bit instruction set. It was not able to run big real application, just small kernels, mini apps. But it got, people interested and started and acquainted with the idea that you could do something with the ARM ecosystems, CPUs. There was a follow-up of the Mont Blanc project. There was Mont Blanc 2, which focuses on the software environment. It was realized that it's good to have some hardware, but hardware without software doesn't give you much. So developing the whole environment, that was a complement to the Mont Blanc project. Mont Blanc 2 went further and I think went well. Mont Blanc 3 was this, and I give you more detail about the underlying processor that was used later on, but it was a follow-up. And this time, the purpose was to deploy some real systems that could be used for actual HPC workloads. So we started working with a company, and we ended up with this prototype that was deployed and was using these Marvell ThunderX2 processors. And so the name was Dibona. Etienne Walter, who is in the room, remember that very well because he was heading the project at the time. So we developed these systems, which and you see the blades here on the central part of the slide, which is the 3 nodes. Each node is with 2 sockets and 2 CPU sockets. And the whole thing is integrated into our top-of-the-line direct liquid cooled system, the Bull Sequana XH2000 at the time. On this, we were able to run full applications. And in that sense, it was successful from, I would say, a technical standpoint. So, but here we're already at the end of 2018. So it's 8 years from this. So depending on your time scale, that's short, but it can be also seen as very long. And then you had another follow-up, Mont Blanc 2020, which was a preparation of the API project, had specifically the development of a NOC network on chip part. And so this was, I think, a smaller project, but I think it was a good step toward the API project. So let me go back a little bit and explain how we ended up with this Marvell ThunderX2 CPU. So, as I said, during the Mont Blanc project and together with Barcelona, but most importantly here with ARM as a partner, we started looking for a potential a system that CPU that we could use in our system, and we met with the Broadcom back in 2013, the end of 2013, and they were developing a CPU codenamed Vulkan, which was very aggressive and very, on the paper, was very, very exciting. Had 32, they were planning 32 cores, so with ARM V8, so that's a 64-bit instruction set, very clean, since with V8 you had the possibility to remove a big part of the legacy 32-bit, and so it was interesting. Quad thread, if you remember, a lot of in the commercial, in the enterprise business, they like this a lot, with very aggressive frequency for the CPU, up to 3 gigahertz. So 750 gigaflop, which was very interesting in that time frame, and a lot of memory. They even, we're talking about Broadcom, they even integrated a 200 gigabits per second NIC, and all of this was supposed to go out at TSMC and 16 nanometer technology, and with a TDP which was above 100, but very interesting for that for the performance that was to be delivered. And it was scheduled for 2015, and you could build 2-socket, 4-socket nodes, so everything was fine. And it was, it would have been quite a match, or even better than what the Intel was planning for in that time frame. So eventually, it was too good to be true, and it didn't happen. And it went through a couple of iterations. It was picked up by Cavium, who's developed a prototype Thunder X, and then Thunder X2. And by the time it became a product, it was handed over to another company, Marvell. And we delivered some of the system with that you see in the picture to one, two of our customers, but it was a little late, and it was, you were talking about after 2018, 19, sorry. It was, by the time it was a product, it was a little too late. There were even follow-ups that were scheduled, but they never materialized. So this was, over 10 years, we went from nothing to having something that was a good prototype, a good demonstration of what was possible. But from a commercial standpoint, I mean, we didn't get it. It was not something that we sold in any volume. One of the reasons for that is, well, when we had this evaluation, so here we're looking at some prototypes this is a slide that internal slide that I fished out, and here is summarized what was the situation with the first prototype of this Thunder X2 back in November 2017. And so we took all the what we had at the time and the other prototypes, so they more or less maybe different. You see KNL, which was something that people were pushing a lot at the time. So depending on the slide, I mean, better is up or down. But you see that on average, if you look at the winner in all categories for all these applications, it was the AMD. And so this was actually AMD came back up in business with a new series of CPUs, Maple, Rome, and so on. And so they were really, they had it, and it was, it was difficult for us and to really get this going as a commercial system. So I went through the what we worked on, but in the meanwhile, since there were a lot of discussion and a lot of projects that started and stopped, we also looked at alternatives. And just to mention a couple, I mean, and there were more discussion, but this one went pretty far. with Qualcomm technology. So it was at the time a spin-off of Qualcomm. Qualcomm was the developer of the Snapdragon, so they felt that they could really go into the server business. And so they started this spin-off QTI. Didn't go very far, but they had some interesting project with 48 ARM CPUs, and well, it was interesting. But before they got to any prototype, they dropped that and they closed down, I think, QTI. But I've heard that they're back again. Another one that we had quite a lot of discussion with, in-depth discussion, was the Fujitsu. They had developed their A64FX system CPU, which was a follow-up of their system that developed the CPU that developed with K, but moved to the ARM instruction set. And we were working with them so that we could integrate the BXI interconnect in their follow-up. So this was, I think, interesting, but it didn't materialize, and Fujitsu and Riken thought that they would go a different path, and so they dropped the A64FX too. And there were others that I'm not able to mention today because of confidentiality, but it was very active. We look at this. We also looked at something I can mention is that Bill in 2014 we looked at this, and we really went pretty far looking at building our own CPU. Our top management canned it right away. They didn't think we had the right size to do this. We tried again a couple of years later after Atos acquired Bill. This guy was also canned by the CEO, who had the very bad memories about the Acri project back in the 90s. And so it says this is Acri all over again, and this was the end of the discussion. You can look at what the Acri project was if you're interested in this. And so then, it was, you cannot do it as your own. The idea was to do it within the API project. And so this is our Cyber, which originally the project was started at Bill Atos, and it was later on moved to this spin-off Cyber. And so again, this is what I officially see in their leaflet. Very interesting, especially in terms of memory bandwidth. And so we know that it's been taped out, and we're all looking forward to the first prototype. Well, the thing is that today, 15 years after the start of this saga, the x86 CPUs are still dominating, and especially with the AMD CPUs, so the Naples, and the Rome, Genoa, and Turin, and the follow-ups. This is something that is well working, and it's difficult to displace. But somehow it looks like the battle, we're fighting the wrong battle, because what's coming with the AI is completely changing the ecosystem, the environment, and the whole ecosystem now is dominated by GPUs for AI, and specifically by one company called NVIDIA. Okay, so maybe a few takeaways since I'm at the end of my time. This was a story at the time, talking about 40 years ago, when I was working in Silicon Valley startups. Is the story goes, how many technology breakthroughs do you need to be successful? 1, 2, or 3? If it's 1, you're not interesting. If it's 3, you're asking too much and you will never make it. And if it's 2, you have to somehow find a balance between being too aggressive and not being aggressive enough. So that was the story. And with this, but this was missing one point, is time. Time, it's definitely not only money, but it's also key to success, and any delay is leading to failure. I mean, if it's become too much. Another thing that really was aware, and this was, for example, the main reason for starting this Mont Blanc 2 was that it was very clear soon that the software was very important, and developing hardware without software was not, was not very, giving you anything. And another thing is the ecosystem inertia. I mean, people think of people as lazy. It's just that it's a lot of things. It's not just that people are lazy, and if you can avoid to do something, I will avoid. But also, I think people don't understand clearly the enormous amount of work that is required to port the software, to optimize the software, and so on. And so this will certainly slow down innovation solutions, and they might even kill it. And for forgetting this, I think you might get into trouble. Finally, so just, I mean, maybe so looking at a more positive, ending with a more positive thought. It looks like it's squaring the square. This is like a squaring the circle, which is impossible. But I think you don't need to be perfect. You just need to get close enough. So that's good enough. So that's probably good. Voila. So with this, I just wanted to thank you. And, so these are my email. They're all still active, Bull, Athos, Evident, and the next one to come. We had a longer story about with the the ARM processors. It's very interesting, and I think that some of this experience people will face again, maybe with the RISC-V, which is getting a lot of interest, or alternative accelerators. You have to face one big contender, which is well in place, and trying to remove them, to displace them. It's a good, interesting challenge, and very exciting from my point of view as a technician, as a technologist. Thank you.
Let's thank our speaker. Thank you very much, Jean-Pierre. We don't have a camera in the room, but trust me, there are others. It's not just, I'm not an AI. Questions for our speaker? I might get us started a bit. So you mentioned this timeline that is at least 15 years of making ARM a valid or viable option for HPC. So I'm making the parallel with the RISC-V world. We have had this chat among ourselves, by the way. So RISC-V probably needs to, the RISC-V ecosystem or people interested in commercializing RISC-V probably need to be aware of this long,
I think
arduous effort, right? If you can comment a bit more on that.
Yeah, and I think you're right. And I made quite a few people mad at me when we had the first discussion in 2017, to be specific, to be precise, when people started proposing this and saying, we could get with the RISC-V, it's great. We can do a lot of things, and we could even be the first exascale in 2020-21. So in 3-4 years. Getting there with an exascale solution, which was be implemented and do production. And in front of the commission, I said, this is madness. With no architecture, you need 10 years to develop. And I think as we have now the new RISC-V timeline unrolling, and we see that there is something that is, as is becoming more realistic, I don't think anyone is expecting that we'll have, even with accelerators, which is simpler than generic CPUs, anything in production before the last I've seen was 2030. So that's 17 years after the initial discussion, 13 years after the initial discussion. So I think this timeline people are aware, even in the RIS5, at least the people I've talked to. And this was actually a discussion that we had at the last API forum in Barcelona last year. So yes, this is it takes a lot of time, and I made the mistake to well, not a mistake. I mean, it's a conscious mistake that you make when you start a project. You always try to present it with the best timing, with the best, assuming that everything is blue sky, that everything will go as planned. And one thing that you see from experience is that there is whatever can go wrong will go wrong. And that the first prototype you come up, the first system, the first CPU, the first accelerator probably won't be the perfect thing, and you would need another iteration. And every time you do this, I mean, you lose time, and your external financing is get shy, and you just. It's not only this, but I worked with other startups and other CPU project in the 80s, and we had the same problem. The first prototype kind of work. It's not the success that you have sold, and when you have to go back to ask for a second round of financing, just people very often your management say okay, but we close it. And so I've seen this several times, and in this story that I was mentioning here, the CPU, this was a kind of exceptional that the CPU went through from Vulkan to the Thunder X, even though it went through 3 different companies, Broadcom, Cavium, Marvell. Eventually, it's one exception. Usually, the plug the project gets unplugged before that, and you stop. So you have to be ready for a long time, and this is something that is difficult to sell to your management and to the people that are financing the project.
Thank you, Jean-Pierre. I think this is a very insightful remark that you made. Questions or comments from the room?
Hi, just a small question. You mentioned the ACLI project, which apparently went bad.
Yeah.
Do you want to share a few insights about things that went bad and maybe helpful for next projects to come?
So the ACRI project was something that well, it's known in France because it was a French project started by a guy named Jacques Stern, who was before starting the project at the end of the 80s, a director at Bull, and got these wonderful ideas about MISD, I think architecture. But the thing is that it was funded by France. It was very good at selling it. So people say, okay, we give you we finance it, and it was France only. So maybe people outside France are not aware of that project. The result of it is that it sucked up all the research funds available at the time to and you build a team from scratch. You put in people, and as the difficulties started mounting, you realize that your first idea is wrong. You come up with a second. You redefine what the project is, and you follow up. And so the project went on for I think 4 or 5 years. In the end, there were never any working silicon. And for a lot of people, it was at least in France, and specifically Monsieur Thierry Breton, who was the CEO of Atos at the time. He was the exact example not to follow. And so this was something that, yeah, was for the people who lived through it. I mean, the people that part of that project, they had a very exciting time, very interesting. But from the outside, he didn't get. He was certainly not successful, and the fact that he took, he pumped all the money for all the other project was something that was not very well accepted. Again, you missed one target, you redefine it, and again, and you never. In this case, it was the worst. That it's like they never produce any silicon, anything working. So some of this, we find in the project, but I think this was very extreme.
Hello, Jean. I want a quick, maybe a little bit off the topic. I mean, not directly from the slides. So based on your experience, how do you see the energy consumption as a metric for the, let's say, next generation's HPC centers? I mean, I see that the power has just made us to lead toward, lower power consumptions, but how do you see the energy consumption? Because I get a feeling it's just more paradoxical, because when you're just designing an accelerator and try to lower the energy consumptions, that basically means you're just making more room for the other applications just filling the data center. So do you think that would be a metric for the HPC to look for, or the power, I mean, the thermal design would be enough?
So just before I answer, I'm just curious who's asking the question. Okay, well, come back to it later. Anyway, if you can still hear me, yes, power consumption is a big parameter of the design, and I would say even more, not only on design of the system, but also on the deployment of the system. And if you look at the data center, that's becoming the most central point, is that the people back in 2010, I mean, they were really pushing the envelope, having a data center that would deliver 4 or 5 megawatt. That seemed to be the extreme case. But as we've seen, for the same class of system, something that would still, for example, in the case of Prace or Zero HPC, would fulfill the same needs. You're now talking about the systems that are 20 megawatt, and there is no end to this. And most, if you look at the accelerators today, I mean, they are going over the kilowatt, and we expect this to double even more, and even more than double in the coming years. So this is really putting a lot of pressure, and you see that big data centers now are teaming up with nuclear plants so that they're able to feed the system. This is, I think, it's an arm race, and in the end, it's as long as people can afford it and they're able to justify it, and this is something that is also not obvious, to justify all these expense. So not only the capex but the opex that is linked to the energy consumption. You would be able to prevent it, especially in the private world. For the more public, I mean, I think people can be a little more cautious about this. In the end, I think what would make the difference is the use, and from an architecture point of view, it makes sense to concentrate things. And so instead of having 10 chips using 100 watts, it's better, it's more efficient to have one using a kilowatt, and to concentrate this with multi-dies and so on. This is fine. I think the biggest part of the solution is in hardware. And if you look at the AI, the quote unquote surprise with DeepSeek, suddenly able to provide a similar level of service with much less power, with a smaller systems, less power, is something that I think is to be thought. Right now, people are just pushing things, and the bigger, the better. I think big push will come from the software and the optimization at that level. It's something that we went through with the HPC and so on. Now, unless we see some revolution in the way we design our chips, I don't think that this trend is. I mean, it will stop at some point because the cooling will become so expensive that you won't be able to do it properly. So at some point there will be a balance there. But so I'm not answering exactly the question. And yes, we missed that. I mean, the people that were quite enthusiastic, and for example, the Mont Blanc project. If you go back and you look at the proposal, was promising a very low consumption but they were forgetting about a few things: the complexity of designing CPUs and they have to all the resources that you need to make them work, and the fact that you need to interconnect, and it's different between having smartphones and having a big system where the application they make all the parts work together.
All right, let's thank our speaker. I think he gave us a lot of things to think about, and all this valuable experience, I think, should be captured. Thank you very much, Jean-Pierre.
Thank you very much. And sorry again, not being able to be there in person, and looking forward to see most of you in Paris in a month.
Okay, yes, at the DPI Forum event.